Okay, welcome. We're gonna continue on here. We've been talking chapter 2, and last time we got into really kind of dimensional analysis, conversions, conversion factors, and equalities. We kind of put all that together since it all really does go together. So when we have something that's an equality, remember that that is basically two values that are on different units, but they do represent really the same sort of quantity of whatever you're dealing with. So again, just a basic sort of equality like 12 inches equals 1 foot. That again represents, as we talked about, the same sort of distance, uh, but they are on different units. And regardless of what type of equality that you're dealing with, you could always write two conversion factors from any equality. And as we talked about, really conversion factors are pretty much just fractions. So to write those conversion factors, we essentially just put one of the units up on top, like in this case, 12 inches, and the other unit on the bottom, like 1 foot. Or we could have a conversion factor where we have 1 foot up on top and 12 inches on the bottom. So these again are two conversion factors that you could use in a problem. As we also talked about, you should probably never use both of them together, otherwise they undo each other. So you should only choose obviously the one that you need to use. We talked about how to set this stuff up, which is dimensional analysis. And when we set things up using dimensional analysis, that is the way that we set up work to basically show the units canceling out. We use conversion factors in this. And really, as we talked about a lot last time, the way that we set those up, it sort of minimizes, in a sense, hopefully some errors that may be made in terms of math. The idea of that is if we have a certain unit that we want to get rid of, even if it's not written as a fraction, we could think of it like a fraction. And remember, when you're doing dimensional analysis, it's all about opposites cancel. So if you want to get rid of a particular unit that you no longer need, you need to put that same unit in the opposite location. So for example, if we had a conversion factor that had unit A in it, we would need to go in the opposite location to get rid of that. And unit B, for example, might be what we're looking for. What we do mathematically when we set it up like this, as we talked about, is anything that is up on top does get multiplied, and anything on the bottom pretty much gets divided. Now, because opposites sort of cancel, all you have to remember when you're doing these things is just put things in opposite locations. Because when we divide essentially unit A by unit A, it becomes 1 and essentially cancels each other out in this particular case. So if we had like 42.5 inches and we want to know how many feet that was, if we're looking for feet, again, we could think of this like a fraction. If it helps you to put it over one, do it so you can see the top and the bottom. You don't necessarily have to do it that way. You could just leave it at 42.5. But again, by seeing that inches are on top, I need to get rid of them. It makes picking the conversion factor pretty simple because everything's written sort of in this top and bottom sort of location. And I know for sure it's got to be that one there on the right. That's going to cancel those. Again, we're going to multiply what we got here. We're going to divide what we got here. And in this particular case, not much to multiply up there on top, but we'll take, if I clear my calculator, 42.5 divided by 12. And that's going to give me on my calculator here 3.541666667. And clearly, the only units left there on top are feet. We obviously never want to give an answer with that many digits, so we want to also think about significant figures here. And the reason when we set things up in dimensional analysis that we only have to think about significant figures is the only operations that you do in dimensional analysis is multiply and divide, which means that is what you should be looking at. Remember that when we use conversion factors, for the most part, a lot of them are considered exact numbers. And the idea with exact numbers is they could have an unlimited number of significant figures. So when we come across something that's considered an exact number, we do not worry about it in terms of the answer and how many significant figures our answer should have. So the only time we really, in a lot of cases, have to worry about sort of a conversion factor is if we cross over from metric to English type conversions. But if you say sort of English to English conversions or metric to metric conversions, they will essentially be an exact number. You don't have to worry about it. The one sort of crossover that is considered, again, an exact number is the one that we saw as well. 1 inch is 2.54 centimeters. So although that is a crossover from, say, metric to English units, that is still considered an exact number, so you don't have to worry about it. So when we look at this, this is considered exact, so we don't need to worry about it. That means a lot of times, this is oftentimes where you're going to be looking for significant figures, but not always the place. And that has 3 significant figures, which means we should come to here, and this should come down to 3.54 feet. Again, a reminder that your calculator does not always give you, obviously, the answer to the correct number of significant figures. If you have more conversions that you need to do, you just kind of keep going down in that pattern of top, bottom, and kind of do that. As we also talked about, typically speaking, if you're looking to solve for one unit by itself, that unit usually ends up on top by itself. It is possible to have 2 units that you need to convert at the same time. And again, keeping things sort of on top and bottom allows you to sort of do the math correctly. And as we also talked about last time, sometimes just taking a more dimensional analysis approach to problems and thinking about units can allow you to bypass perhaps thinking about a formula or rearranging a formula. I'm not sure if you're, should be dividing or multiplying. So it kind of takes the guesswork out of the math part of it if you kind of set it up this way. Any questions on any of that stuff there? Okay. Obviously, if we did come across, though, a conversion that we needed to use between metric and English, we would look at, in most cases, the number that is a real number, if you will, rather than the one of that kind of conversion factor. So usually there's like a 1 and then some other number. So we would look at, obviously, the non-1 number to think about significant figures. Other places where we do want to look at significant figures, where we do use conversion factors, as we talked about before, is sometimes in problems you are given some information that's really not a true conversion, but specific for that problem. Like, for example, I think maybe we did how fast you were driving miles per hour or something like that. Those type of values that are given to you, you do typically need to look at the significant figures in those numbers when you're kind of doing the calculation. Any questions on that there? All right, so let's take a look at some of this that we kind of talked about. So again, metric conversions here, 1 meter is 100 centimeters. Once again, going to give us our 2 conversion factors there, 100 centimeters over 1 meter, or you can flip it 1 meter over 100 centimeters. This is our metric to English conversion. And again, we have our 2.2 pounds over 1 kilogram, or 1 kilogram over 2.2 pounds. So again, that's a crossover conversion. So we would be looking, as I mentioned before, at this number here, not the 1, if we had to think about significant figures. So that would be considered 3 significant figures if we need to use that conversion factor in a calculation. All right, so let's just take a look at these here. We also talked about as well that you can find multiple pathways, for example, to go in a conversion problem. And, there's not necessarily a right pathway or a wrong pathway. Sometimes the best approach is try to find the simplest way to get there. But it is possible 2 people doing the same conversion use different conversion factors and end up at the same answer, hopefully. So it is possible more than one way to kind of get there sometimes. So again, here's our equalities. Our 1 liter is 1,000 milliliters. And again, that is definitely an equality and conversion factors that we use a lot in chemistry. The liters to milliliters conversion and backwards. Inches to meters there, and that's a prefix to prefix. This is the direct sort of conversion. And we also touched upon that last time as well. Remember that if you are kind of going prefix to prefix, best to go to the base unit and then back to the next prefix is probably the better way of doing that, because you definitely will have access to that, like, kilos 10 to the 3 or whatever it may be, type of chart. So you could do that. So you kind of want to go to that base unit and then back to the next prefix unit. Now, as I mentioned before, sometimes, like I mentioned, you are given some information in the actual problem that you would use as a conversion factor. So for example, here, again, a car traveling 85 kilometers per hour. Again, what that means is you go 85 kilometers in 1 hour, which gives us one of our conversion factors. And we could in 1 hour go 85 kilometers, and this would be the equality here. Here, if we were to use this again in a actual problem, we would need to look up the significant figures in these numbers here, and it would be the 85 that we would look at here, and it would have two significant figures. So again, you don't want to gloss over all conversion factors. There definitely are some that you do need to look at. Another example here, a tablet contains 500 milligrams of vitamin C. The equality would be 1 tablet is equal to 500 milligrams, and that gives us our two conversion factors here, 500 milligrams vitamin C in 1 tablet. Our 1 tablet is 500 milligrams. That also would need to be looked at if you were using that, as obviously a tablet could be 250 milligrams, right? So it's not always 500 milligrams. So again, that is specific here. The way this is technically written, it has only one significant figure, and that would be the number that we would want to look at. Again, here we wouldn't really be looking at the 1 tablet, as obviously that is something like, like an apple or something like that, that would be kind of considered more of like an exact sort of number and stuff. Now, super common in chemistry is we're oftentimes given information in percentages, and sometimes people mess up with percentages because they are in percentages. So the best thing to do is kind of turn percentages into some type of usable conversion factor. And the best way to turn percentages into sort of usable numbers is to really keep it simple. And that is just assume you have 100 of whatever you're dealing with. And if you assume you have 100 of whatever you're dealing with, basically the percentage number stays the same, right? So you could very easily convert that. So here, for example, we have 18% body fat by mass. That means, for example, one version of that is 18 kilograms of body fat and 100 kilograms of body mass. And again, basically just assume 100 and you have 18 kilograms out of 100. Again, you could also do that with pounds if you wanted to in this sort of situation. And that would mean that there is 18 pounds of body fat per 100 pounds, right, of body mass. So you can use any sort of unit and just assume that you have 100. Once again, here we would want to look at the 18 in this particular case. And that 18 does have two significant figures. Again, we would probably look at just the 18 here because it originated from the 18%, where that 18% had two numbers or two significant figures in that case. Any questions on that? Now, again, doses is also sort of the same situation here. We have one capsule of Keflex is 250 milligrams. And again, giving us our two sort of usable conversion factors. Once again, here we would look at the 250 having two significant figures. And obviously here again, the one capsule, like our 1 tablet, kind of would be more of an exact number. We wouldn't worry about that particular number. All right. So I think we're going to kind of skip through those here. So we've touched upon problem solving, which again is dimensional analysis, and we definitely want to make sure that we do set up everything sort of correctly, showing that work. So why don't you give this a go? If a person weighs 178 pounds, what is the body mass in kilograms? So a couple of equalities that might be helpful. 1 pound is 453.6 grams. And kilo, right, is 10 to the 3. So why don't you take a moment, set it up using dimensional analysis and see what you come up with here. look. And again, like I said before, there are multiple ways you could do this. I happen to, just off the top of my head, remember these conversions, which will get me there. There is definitely a direct conversion you could do, as we saw just a second ago, the pounds directly to kilograms. Again, they all should get you to the same spot. But since I wrote these on here, let's do this one and take a look at it. So remember here, we want to get to kilograms. We got pounds. So we got 178 pounds we're going to start with. Again, you don't need to write it over one, but if it helps you just kind of visualize top and bottom, it's a good idea. From this equality here, obviously I could have two conversion factors, my 1 pound over 453.6 grams, or 453.6 grams over 1 pound. And obviously kilo, right, means 10 to the 3. So again, a reminder how to use that properly. That is how much there is in the base unit to one of the prefix units. So here, our base unit is grams and our prefix is kilograms. So basically 1 kilogram would be 10 to the 3 grams. Our 1,000 grams is a kilogram. So again, that also is the same thing. So again, you want to make sure that you use that right, like we talked about the other day. That also gives you a couple of conversion factors you could use. 1 kilogram over 10 to the 3 grams, or 10 to the 3 grams over 1 kilogram. A reminder again that that is 1 times 10 to the 3. If you needed to punch that into your calculator, again, making sure you use your exponent button. So in this case, I'll just rewrite it over here. I'm going to start with the 178 pounds. Again, I know it's on top, so we want to go opposites to get rid of pounds. And that's going to be the conversion factor here. That's going to allow me to do it based on what I chose. And at this point, if I stop the calculation right now, I have pounds on top and pounds on the bottom, and they are going to cancel and leave me with grams if I were to kind of stop the calculation at this point. That is not really where I want to go. So I did go obviously here from pounds to grams. I then want to go from grams to kilograms. So that is the next conversion I want to kind of do. Again, setting it up with dimensional analysis, it should be really clear to you. Grams in my case are up on top, which means I need to go opposite to get rid of it. And that's going to put my grams on the bottom, which should be this conversion factor here. Gives me 1 kilogram, 10 to the 3 grams, gram on top, gram on the bottom. Cancels. The only unit left now are kilograms up on top, which is what we're looking for. Here we're going to once again multiply whatever is up on top. Remember, we want to hit the equal button on our calculator there when we're done. We then will come back and divide what's on the bottom. You don't really have to divide the 1, but you do want to make sure if you have multiple things on the bottom, you do hit that equal button multiple times. So if I do all that, I'm going to go 178 point nothing, 178 no point, times 453.6. I'm going to hit equals. I'm going to divide it by basically 1 times 10 to the 3, or 1,000 basically. And we're going to do that and not put negative. There we go. And that's going to give me here on my calculator 80.7408 kilograms. First off, any questions on the setup here? Now we want to look at significant figures. So do I need to worry about this one in terms of significant figures in my answer? I don't, right? Again, that's a metric to metric, so that's all good. You don't have to worry about that. How about over here? Should I worry about this one? Technically, I should. That is a metric to English conversion, right? The number I should look at in this case is this top one, right? So that has technically 4 significant figures, right? I should also look over here at my original number always, and that has 3 significant figures. That means my answer should end up with 3 significant figures. That puts me to the 7 here. And we got like an 80.7 kilograms, cleaned up a little bit. Any questions on that there? So obviously here you can see, doesn't really matter your sort of version there or way, but again, if you wanted to, I think we have the other way you could have also have done this one. This is your kind of direct conversion, which if you remember that one or found that one, would also work. We have the 2.2 pounds equal 1 kilogram, and it gives us our 2 conversion factors. We set it up. And you can see really the only difference is slightly different because we use a slightly different conversion factor, but pretty much the same answer. Here, do we need to worry about the significant figures there between the pounds and the kilograms? The answer is, as you can see up there, yes, right? Again, that is a metric to English conversion. And here we would look at the 2.2, which is 3 significant figures, our original number, 3 significant figures. And we end up basically with the same 3 significant figures as we did in the previous one. Any questions on either of those ways? Yeah. On the test or anything like that, you're all good as long as whatever you choose is a legitimate conversion that you didn't make up. And like I said, there are multiple ways you could get to the same answer depending on sort of what pathway you choose, what maybe conversion factors you see. Sometimes people, if they look at a chart, will kind of just pick up like the first one they see and kind of go that route, while there might be perhaps a more straightforward one that you could do. So as long as whatever you choose is, again, not one that you made up, a legitimate conversion equality, you could do it whichever way you want to go there. Yeah. You should always show the work no matter what. Yeah. So just so we're clear, good question. For full credit, obviously, on any type of problem that you would be doing on an exam or quiz, you do need to show pretty much this. Yeah. This bottom part here. So pretty much the dimensional analysis set up, the units on everything canceling, and then obviously your answer to the proper number of significant figures. If it helps you to do all the rest, do all the rest. It doesn't really matter to me, but to get full credit and you did it right, you got to show what's on the bottom there, basically, always. Yeah. And as we've been seeing here and as we've been talking about, you definitely want to show your work with the dimensional analysis, and you want to kind of do it correctly in a sense. So sometimes people show the units, but they do it more like a side-by-side type of conversion. They just kind of do that. And then again, they do like a kilogram. And then at some point, they're really not sure, should they be multiplying, dividing, because there's kind of no real good top and bottom. So if you keep it written pretty vertical in that sense, top and bottom, it just makes it much easier, and you keep track of the units. You don't end up multiplying in some cases when you should be dividing, or vice versa in that case. Yeah. Other questions? All right, so here we want to know how long or how many centimeters is a 2.44 meter rattlesnake. That doesn't sound fun, so we'll go with centi. Centi again, just for some practice here, 10 to the minus 2. So give it a go, see what you come up with. Mhm. Are you talking about this right here? Yeah, so it's it is exact and significant figures. So because it's over, the exact that they're talking about is the 1 part of it. The 2.20 is the 3 significant figures.
Oh.
Yeah. So within sort of a metric to English conversion like that, a lot of times you'll have 1 as one of the numbers, the number 1 as one of the numbers, and that's sort of considered exact. And the other sort of part of that conversion factor is usually the number you want to look at in terms of significant figures.
Not the same case inch.
Yeah, so in the case of like 12 inches is 1 foot, they're both considered basically exact numbers, so you don't have to worry about either of those. Okay, so once again, we want to make sure that we use this correctly. So in this case, we're looking at meters, and meters is our base unit. So once again, that means there's 10 to the minus 2 meters in one of the prefix units, which is a centimeter. That gives us 1 centimeter over 10 to the minus 2 meters, or 10 to the minus 2 meters over 1 centimeter. So again, we're going to start with our 2.44 meters. We're going to go opposite here. So meters are up on top. So to get rid of it, we are going to go in the opposite location here where meters are on the bottom. 10 to the minus 2 meters, 1 centimeter, if I get it there. And that means we're going to basically take 2.44 divided by 1 times 10 to the minus 2. That's going to give us 244 centimeters in this case. This is a metric to metric, which means they're both good. They're both exact. This is the only number we really have to look at in this case, which is 3 significant figures in this case. So our answer should have 3 significant figures. Any questions on that one there? Okay. All right. Hopefully they agree. They do. That's good. All right. So obviously, sometimes we do have more than one sort of conversion factor that we need to use. And for example, here, if we had a doctor ordered and prescribed a dosage of 0.15 milligrams, if they only come basically in 50 microgram tablets, how many tablets will need to be used? So this is one of those places where we are going to get sort of our conversion factor out of the actual problem itself. That basically means there's that micro weird symbol. So this is one tablet has 50 micrograms and we're looking for milligrams, right? So the idea here is we have 0.15 milligrams and our tablet is 50 micrograms here. I'm just going to use that symbol there. Equals 1 tablet, right? So we definitely could use this as a conversion factor of 50 micrograms over 1 tablet, or 1 tablet is 50 micrograms, right? The problem though is when we talk about sort of the doses there, the milligrams and our micrograms are different units, right? So they're not the same prefix, which means we cannot just jump right in there and use it. So the idea here is you need to get basically these units to be the same, sort of the gram units, if you will, before you could kind of use them together. It is really your call. You could, if you wanted to, convert that into milligrams, or you could convert this into micrograms. They both, again, should come out the same. It's just your preference. I'm personally, since I just got one number here, I'm going to take this to micrograms first. And then that will allow me then to use, obviously, my conversion factor here to figure out how many tablets I need to give the person. Now, this is, again, technically a milligram to microgram conversion. And although we saw it a second ago, I'm still going to do it like I said before. My route to get there is going to go milligrams back to grams to micrograms, again, using that base unit to get us there. The reason we want to do that is because we could look on that chart and we could look up our milli, and we could see that our milli is 10 to the minus 3 there. And we could also look up our micro and we could see that that's 10 to the minus 6. So these sort of conversions we can find really easy on a chart. And again, you're not going to have like Google available to you to try to figure out the direct conversion if you don't know it. So this you probably would have available to you. So again, doing it to the base unit and take it from the base unit to the next one is probably a really good approach. So what does all these things mean? It's a good question, but they mean in this case, in 1 milligram, I would have 10 to the minus 3 grams, which we could use as our equality to go from milligrams to grams. That would take us step 1 here. Step 2, we could then use the other one, which means in 1 microgram, there is 10 to the minus 6 grams, and that's what's going to allow us to get over to sort of the last spot that we need. So I'm going to do that first. So I'm going to start with my 0.15 milligrams. Again, going to do dimensional analysis so I don't have to think too much about it. If I want to write the conversion factors, I could. If I don't, I just need to put things in the right spot, really, right? So my milligrams here are up on top, which means on the bottom needs to go milligrams, right? The opposite. And up on top needs to go our grams. If I stop right at this point, I am now in grams. And I got that from this equality, right? So I don't necessarily have to write the conversion factors if I don't really want to. I have it still set up in dimensional analysis way. And again, I could clearly see grams are up on top, which means when I take it the rest of the way there with our micrograms, what units should go on the bottom? Micrograms or grams? Grams. So I'm going to come over to the equality that I need, and that is grams. So that should go on the bottom. And this guy up here should go up on top. Once again, opposites will cancel. The only unit I have left at this point is micrograms. First off, any question on that there? Again, we're still going to multiply. So we're going to take 0.150. We're going to times it by basically 1 times 10 to the minus 3. And that we're going to hit equals. And when we do that, we're then going to divide it by what's on the bottom. So we're going to multiply and divide. And we're going to divide by 1 times 10 to the minus 6, basically. So the minus 6. And that's going to give me 150 micrograms at this point. First off, any questions on that, by the way? By the way, just significant figure-wise, what should I end up with in terms of significant figures? Should I worry about this conversion? No, that's metric to metric. Should I worry about this one? No, I should worry about this one, right? That has how many significant figures? 3, which means really my answer should have 3, right? Does it have 3, by the way I wrote it? It doesn't. It actually only has 2, right? Does it have 3 now? Yeah, with the decimal point there at the end, now it has 3, right? So you do want to kind of keep track of that because we're now going to kind of use that number and continue on with our calculation. Now that we have it in micrograms, we could definitely use our equality or conversion that was given to us in the problem, right? And again, you could actually just continue on here if you like. We're going to do the same thing that we always do, which is I know I want to get rid of micrograms, right? So micrograms should go top or bottom. I want to, where? If I want to get rid of micrograms, it needs to go bottom because right now it's on top, right? So it does need to go on the bottom. That's going to leave me a tablet up on top, which seems good. And 50 micrograms there with a dot, I think. And we're going to go 150 divided by 50. That's going to give us technically 3 tablets in this case. And if we want to be sort of nicely significant figures, 3.0 tablets would be the right sig figs because this guy has 2 significant figures because there is a decimal point there, I believe. And this one has 3 significant figures, which means technically 3.0 tablets. Although in most cases, you probably wouldn't break a tablet apart if you're giving that to somebody, I imagine. So you might just go with a 3. But significant figure wise, it should actually be 3.0 tablets based on the 2 significant figures from this conversion right here. Yeah. Any questions on that? So that is a very common thing that people mess up on, which is they have a conversion factor given to them sometimes, and they have another value that they need to use it with, but they're in different units. So remember, things do not cancel out if they are not the exact same unit. So sometimes you do have to do a little work before you use a conversion factor so that you actually can use a conversion factor correctly and all the units cancel out. Any questions on that? There you go, 3 tablets, not too bad. All right, we know days, hopefully. All right. So let's just say here we're going 65 meters per minute. How many minutes would it take you to go 7.5 kilometers? Again, kilo is our 10 to the 3. So set it up, see what you come up with. We're looking for how many minutes would it take you? While we're at it, why don't we just also do, I don't know, let's do how many seconds as well, yeah? How many minutes and how many seconds would it take you if you Okay, so let's take a look. So once again, here we are given an equality or conversion factor in the actual problem, and that's 65 meters per minute. That's basically a rate, right? And a rate is a distance per time, right? And that's really what can be used to convert a distance into time, or obviously if you have time into a distance, depending on which way you're kind of going. In this case, we have a distance and we want to know a time. So we're going to use that as a conversion factor. And basically what that means is got 65 meters in 1 minute. Gives us our two conversion factors that we could use. 65 meters over a minute, or a minute is 65 meters. Once again, we run into the same situation we had on the last one. My distance here is kilometers, but my distance in my conversion factor is meters. So we cannot use them like that. Otherwise, we will be off by a factor of like 1,000 in this particular case. So again, you do need to do a conversion. It doesn't matter which one you choose. Again, I'm going to take just the one number by itself there to 7.5 kilometers, and I'm going to take it into, not that, but I'm going to take it somewhere. There you go. I'm going to take it into 7.5 kilometer. I'm going to take it into meters. And once I do that, I am good to go with this conversion factor basically to use it. So again, in this case, we're dealing with kilometers and meters using our kilo conversion. That means in one of the prefix, which is kilometers, there's 10 to the 3 meters. So again, that is the equality that we could use. That also will give us a couple of conversion factors to use. And we can now do our conversion that we need, 7.5 kilometers. Once again, that we just need to recognize is up on top. So opposites here to cancel. So looking at my conversion factor here, or really my equality. In this case, kilometers are on the top. That means kilometers need to go in the opposite location, and our 10 to the 3 meters goes up on top. That way they cancel. Once again, we're multiplying and dividing on the bottom. So we're going to take basically 7.5 times 10 to the 3, or 1,000. That is going to give us 7,500 meters in this case. Significant figure wise, actually, at this point, we're actually good significant figure wise. That is an exact conversion, so we don't have to worry about it. Our original number had 2, and my 7,500 there has 2. Any questions on that so far? Again, the reason we need to do that is what's going to open up us being able to use really the conversion factor that was given to us and now go from distance to time. And I could do that by taking my 7,500 meters. And once again, all we have to remember is opposites cancel. That is meters that technically is up on top, which means meters here does need to go on the bottom in this particular case. That would give me 1 minute is 65 meters. The meters would cancel. And at this point here, we would have 7,500 divided by 65. Going to get here a 115.3846 minutes. Significant figures. Do I need to worry about the 65? Do I need to look at that? The answer is yes. Again, this is a conversion that's given to you. So we do need to look at that, which is 2 significant figures. And this is still 2 significant figures. That means right about there, right, is where we should end. And we do need to round up because of the 5 that we have next door. Does become 120 minutes, right? No decimal. Otherwise, that is 3 significant figures at this point. Yeah. Question on that there. We also did seconds. So we should hopefully know, we talked about it a couple of times, right? There are 60 seconds, I think, in a minute, right? Still. So we'll take our rounded number, why not, since we have it, minutes. And again, we could do the same thing here. Assume it's on top, as we can see. So minutes need to go on the bottom. So 1 minute would be our 60 seconds. Minutes will cancel. Going to leave us seconds. And if I take that and times it by 60, just so you know, I'm actually multiplying it by the non-rounded number on my calculator, which is a good idea since we're looking for that. 69.23 seconds. Here we should still be at 2 significant figures, so a little 6,900 seconds at this point, which again is a little bit different than what you would get if you didn't do that. So if you didn't use the rounded number, you would end up with 7,200 seconds here. So I'll just go with the rounded number there since we use it on the setup. Any questions on that? I would take either, by the way. I'd probably, if I were doing it all the way through, I probably would end up with the 6,900, but I would take 7,200 if you use a round number. Any questions on either of those there? So like I said, very common error, trying to use a conversion factor with the wrong units that won't cancel. You just got to watch that you're not just automatically just using the conversion factor without everything being correct. Any questions on that there? All right. All right, so let's try some here. You go to local AM PM, you get yourself 32 fluid ounce drink of Diet Coke from the Thirst Oasis. Crushed ice, cubed ice. Everybody knows it's crushed ice, right? And you want to know how many gallons of Diet Coke you drank. There's some equalities that might be helpful for you. Here's some conversion factors that might be helpful for you. So set it up with dimensional analysis. Get yourself an answer, see what you come up with. And so again, you can find a couple different ways you probably get there. One pathway that I chose here based on my equalities is I could take it from fluid ounces to quarts. And once I have it in quarts, I could then take it to gallons using my equalities to get me there. Once again, we're going to start with my 32 fluid ounces here. Again, it is basically up on top. If you want to write the one underneath it to help you out, you can. That means when I go to my choice here, my first set of conversion factors, we want to go opposite. I should use the one on the left or the one on the right in this case. Should use the one on the left as it has the fluid ounces on the opposite location. So 1 quart up on top, 32 fluid ounces on the bottom. At this point, the fluid ounces and fluid ounces would cancel. I am left with quarts that's up on top. And again, that's good to know because it makes my next conversion pretty simple. I should use the one on the left or the one on the right here. Quarts are up on top, which means I need the one on the right that has quarts in the opposite location to get rid of them because we don't want quarts. We do want to end up with gallons up on top, and that will get rid of my quarts. So if I do all that good stuff there, we end up with a number, 1 divided by 4. We end up with 0.25 gallons in this case. And by the way, you do not end up with 1/4 because that makes me think you're just too lazy to divide it. Yeah. So don't leave your answer as a fraction. Get an actual number, decimal, write sig figs, all that good stuff. Not too bad in this case, but I've had people write 323 miles over 5,268 hours. Looks good. So don't do that. Don't leave answers as fractions and stuff like that. Make sure you actually divide it out. In this case, significant figure wise, really kind of the only number there we're going to look at, which is 2. And there we end up with 2 sig figs there for our answer. Any questions on that one there? Once again, for full credit, we're looking for what we see here on the bottom. Yeah, this is what you need to show. Yeah. Yeah. Again, there are different ways you could do it, so you could combo it. Yeah, so as long as it's all good, it should be okay. Yeah. All right. All right, we'll actually skip this one. We did one kind of similar a second ago. I think we're going to go to, let's do this one. You're stranded 125 miles away from home. You decide, nice day, let's go for a walk. You walk 55 feet per minute. How many days will you be walking? Hopefully it's nice all those days. Okay. All right, so some equalities that might be helpful for you. So set it up dimensional analysis. Figure out how many days it's going to take you to get home. So let's take a look and see. So kind of a similar situation to one we saw a second ago. Here we have a distance that's in miles, and we have a rate, which is basically a distance over time. And again, that rate is what's going to allow us to go from, in this case, distance to time, since we are looking for days, which is a unit of time. We have the same situation as we talked about earlier. My distance here is in miles, but my distance here is in feet. So the way it sits there, they are not usable together unless you do a conversion. And again, as I mentioned before, it does not matter. You could either take the miles to feet or the feet to miles. I am going to take the miles to feet here and then just use this as a conversion factor. Obviously, that was given to us right there in the problem as a conversion factor. And I don't know what it says on your handout, but hopefully it says 55.0. I hope so. That's what we see here. So I'm going to use my miles here to feet equality and conversion factors to do that. So I'm going to start with that 125 miles. That is technically on top, even though I'm not writing it as a fraction. So again, a reminder, those miles are up on top, right? So when you start with just one number by itself, it's basically on top. And we want to go opposite. So again, to cancel, we want to get rid of miles. That has to go on the bottom. My 5,280 feet need to go on top. And the miles here will cancel. That's going to give me a whopping 660,000 feet. Definitely can get your steps in today, I suppose. Yes. So now that I have it in feet, I am good to go with my conversion factor, which can be used as 55 feet per minute. Or on top, you could do a minute is 55 feet. Again, you could use it as a conversion factor either way, whichever way you're going to need to do it. I'm going to continue on here with my number there, 660,000, a couple more zeros, feet. Once again, not written as a fraction, but the feet are on top, which is really important because now it should make my decision pretty simple. I need the feet in the opposite location, which is on the bottom. That move right there is going to allow us to go from distance to time, basically here. That's going to give us 55 feet per minute. Feet on top and feet on the bottom will cancel. If I laid up the calculation right at this point, I am in units of minutes, which is good because we're at least in time, but we do want to get to days, right? So again, there's multiple ways you could get there, but we'll just go step by step. So again, minutes to hours in this case is what we're going to do next. Minutes are on top, so that means 60 minutes should go on the bottom. 1 hour should go on top. Minutes will cancel. And if I stopped right at this point, the units I am left with is hours, which is on top. Getting close to what I need. Hours now to days, right? Will get us there. And again, we talked about only 24 hours, right, in a day. So the nice thing again about setting up like this, there should be no misunderstanding. Hours are clearly up on top, right? So again, to get rid of them, we need to put the hours on the bottom opposite location. And 1 day up on top. Hours will cancel, going to leave us only days left, which is good. Once again, we are multiplying whatever's on top, however much we got, and we're dividing by what's on the bottom. Now, a reminder here, you want to be careful when you punch this in. There's really not much to multiply up on top since they're all basically ones, right? These are all basically ones up on top. We want to divide by the bottom, which is 55. After you do that, hit the equals. Yeah. Then you want to divide by 60. After you do that, hit your equals button. And then you want to divide by 24, hit your equals button. And you will get the right answer, hopefully. Again, if you try to punch all that in at once and you are not very careful, you will get the wrong answer. Yeah. So if you want the right answer, do it like that, and you'll probably be in good shape. Let's talk about a couple things like sig figs. I don't have to worry about this, right? I don't have to worry about this. Should I worry about this? I should. And this has 3 significant figures. Should I worry about this number? I should, but I should not worry about that number there. I should actually worry more so back this way, yes? And that number really had 3 significant figures, right? Which means even though I didn't write it with 3 significant figures, this number here should technically still have 3 significant figures, which means down here, technically, that number should have 3 significant figures, which means my answer should technically be 3 significant figures, yeah. And 8.33 days. That's a long walk. Hopefully, no stopping, I suppose. First off, any questions on that? Can't tell you how many people will do this problem or a problem like it and end up multiplying the 60 and the 24 when they should be dividing. So again, setting it up like this where you can clearly see top and bottom, remembering top you multiply, bottom you divide, you will hopefully do the right thing. Again, if you kind of do not set it up like that, you will probably not get the right answer. And you should set it up obviously like that. It helps with the math, and you're supposed to show your work that way as well. Question on conversions, dimensional. Okay, any questions again on dimensional analysis, conversions? Again, you need to show your work that way. And as we talked about, it's probably a great idea to, when possible, just take a dimensional analysis approach. Again, it really does sort of simplify everything, simplify the sort of equation, the rearranging, and it can be very helpful. All right, now to finish up the last part here of this chapter. Hopefully, maybe, there it is. All right, the last thing we're going to talk about is density. And the density of an object is basically a property that determines, for example, whether or not a object will sink or float, say, in water. So, for example, or any substance really, if a substance is more dense than water, then it will sink. And if it is less dense than water, it will actually float. The density of liquid water is an important number to know because sometimes you do need that. So, and for the most part, you can use it as 1 gram per milliliter. So if you ever find yourself in a problem where technically you need the density of water, that is basically the number that you should use. By the way, just so you know, density does change with temperature. So, if it happens to be a specific temperature, it can change. But I would say 99 times out of 100, if you're doing a problem and you need a density of water, that's probably the number you should lay up for liquid water. When we look at these things here, we can see that water there is 1 gram per milliliter. We have ice cubes, right, which is actually water as well. So ice, which is water in the solid state, is actually less dense than liquid water. And that's an unusual property for a substance. In most cases, things in their solid state is more dense than their liquid state, right? They could get in there really tight. The difference with water is when water tries to freeze, or when water does freeze, not just tries, because it doesn't have as much energy and water molecules are basically held together through what are known as hydrogen bonding. When a bunch of water molecules come in to basically freeze, it creates a lot of really open space between the different water molecules, kind of swells it, if you will. And basically what that does, it actually lowers the density of ice. And that's, again, a very unusual sort of property. Usually it's the opposite. You're really more dense a lot of times in your solid state than in your sort of liquid state. So you see there's some pieces of aluminum and lead are more dense than liquid water, so it is floating. The formula for density is D is equal to M over V. That is mass over volume. As I mentioned a second ago, typical units of density are grams per milliliter, are grams per cubic centimeter. These are the typical units for solids and liquids. If you're dealing with gases, which we really don't at all in this class, but sometimes you might come across it, the density of gases are typically given in grams per liter is typically what they're given in. But these are going to be your big 2 units for density here, grams per milliliter or grams per cubic centimeter. A reminder that 1 milliliter is equal to 1 cubic centimeter, right? It is a sort of 1-to-1 conversion. How do you get a cubic centimeter? As we talked about when we were talking about volume, if you have the length times the width times the height, and you measure each of those, say, in centimeters, and you multiply them together, you get cubic centimeters, which is a volume. Each of those individual measurements are actually length measurements. But when you have something like, say, a solid wooden cube or something like that, and you take those measurements and you multiply them together, you get cubic centimeters, which again is a volume. Clearly, milliliters you could get very simply by filling something in a graduated cylinder, for example, and taking a volume reading is one way that you could do that. Now, this equation is something that you should know how to rearrange, and you should know it might not be provided for you, probably not. So volume in this case would be mass divided by density, and we get that basically by multiplying volume to both sides and then dividing by density to both sides. Those cancel, and we end up with what we got on the bottom. Now, if you want the mass is equal to volume times the density. And those are kind of three ways you could rearrange this equation. Some people like to remember the DMV triangle because everybody loves the DMV, right? And density is mass over volume. Volume is mass over density, and mass is volume times density. So you remember the DMV triangle, and you could rearrange that pretty easily in this case. Any questions on that there? Now, when we have things that have a very high density, they typically are packed together pretty tight to one another. When we have things that are lower in density, they're not as packed in to one another. By the way, if I had different volumes of liquids that had different densities, they would typically separate out by layers, basically, right? So you would have different layers that would occur if you put some solutions of different densities together. Obviously, the bottom layer would be more dense. Obviously, the top layer there would be less dense. And if you put something in it that just kind of floats right about there, that means that whatever that dot is more dense than whatever's above it in terms of layers, and it is less dense, right, than anything below it as well, right? So it just kind of suspend itself sort of in that layer. Right. So as I mentioned before, typical units there, grams per cubic centimeters, grams per milliliters are grams per liter, right? Same idea if you take a bucket of water and you take a Diet Coke can and a regular Coke, right? And you put them in there, will they both sink? Will they both float? Will they do one of each? It's a good party trick. I know Super Bowl was yesterday, but it's a good party trick anyways, right? So actually one will sink, one will float. Which one was going to sink, you think? The regular Coke. It has a lot of sugar in it, yeah, making it more dense. Diet Coke's got artificial sweetener, not so much sugar, right? So it actually is less dense. So the Diet Coke would actually float, and the regular Coke would actually sink in that case because of the sugar. Here's some density of some common objects. As I mentioned before, water is usually the one that we look at and use at 4 degrees Celsius, which is actually the maximum density that occurs. That's also why, for example, water freezes from the bottom up or the top down, like in a lake or body of water like that. It freezes from the top down, right? Otherwise, the fish are in trouble, right? If it freezes from the bottom up. And that's because what ends up happening is your warmer water, like your 4-degree water, sinks because it's more dense. Your cooler water actually goes to the top where it actually freezes, right? And usually sometimes it doesn't freeze so good, which is why they tell you not to walk on it, right? Because it will crack and you'll be in real, very cold water down there, right? And stuff like that. So that's why fish is right and everybody's okay when it freezes, right? Because it does freeze from the top down, not the bottom up. It has to do with density of the different water sort of temperature. All right. Now, as I mentioned, there's two common ways to sort of get volume, especially when you're dealing with density. So as I just mentioned before, you can do some length measurements. You clearly could just put a liquid in a graduated cylinder, right? Read the meniscus. very badly drawn meniscus there, and you can take a volume reading. The other really common way that we get the volume of an object is volume by displacement. And the idea of volume by displacement is this. You take a certain amount of a liquid like water, and you put it into, say, a graduated cylinder, and you take an initial reading of that liquid. You take a solid object, such as this, and you basically put it into that graduated cylinder that has the same water in it. And what's going to happen when you do that is the water level will go up or down. Will go up, yeah? So, and basically what will happen in this particular case is the object will displace a volume that's equal to itself, its own volume, basically. So we can very simply in this thing, which is a very common density sort of lab, if you take the difference in the final volume versus the initial volume, that will give you the volume of the object that you put in there. So the volume of the object is typically the final volume minus the initial volume. And you'll be able to very easily, like a rubber stopper, whatever it may be, a solid, whatever you want to dump in there, you can very easily figure out the volume. And clearly, that's easy to do. And you could just take the solid to a balance and put it up there and get the mass of it. Probably before it goes for a swim would be good, so it's not wet. And then you'll have the mass and you'll have the volume. You could then go into the density equation, obviously, and calculate the density by doing so. So in this case, the density of zinc, we have our mass of the zinc in this example, which you can get from the balance, as you can see there. We have our final minus initial reading here, which gives us our volume. Again, mass divided by volume. This is also really important here. A couple of things, which is here we're looking at 4 significant figures. Here we're subtracting, which means we're looking at decimal places, right? And we should go to 1 decimal place. And in that case, as you can see there, you get 9.5 milliliters. Although that has 1 decimal place, how many significant figures does it have? It has 2 significant figures, right? And that is why our answer will end up with 2 significant figures. So again, you want to be careful as you're doing it. And again, in this case with density, you sometimes will be doing subtraction and then doing some dividing or multiplying. So you do want to, again, keep track of those significant figures throughout your calculation. So those are 3 very common ways that you could get a volume. Just take a reading, take some length measurements, or again, do volume by displacement to figure out the volume of a solid. Any questions on that there? All right. So why don't you give this a go? What is the density in grams per milliliter of a 48-gram sample of a metal that when placed in a graduated cylinder that has 25 mils of water goes to 33 mils? See what you come up with here. Okay, so clearly in this case, we're dealing with density. So we should think about our density equation. Density is mass divided by volume. Oftentimes, a really good practice is to pull out the information and see what you have. It'll kind of maybe point you in the right direction if you're not sure. Obviously, here we have the mass given to us, which is 48 grams. We have an initial volume of 25 milliliters before we put the object in there. We have a final volume of 33 milliliters. So ultimately, we do have a volume, we do have a mass, so we can solve for obviously our density in this case. We do need to figure out our volume, and again, it is basically the difference there, right, between where it started and where it ended. So the volume of our object going to be our final volume minus our initial volume. So we're going to go 33 milliliters minus our 25 milliliters. And that's going to give us 8.0 milliliters. Here we do need 8.0 because we are subtracting and we are looking at decimal places. So that's 1 decimal place, 2 decimal places. We need the 8.0 for the correct answer there, not just 8, because 8.0 has, in this case now, 2 significant figures, which is going to play a pretty big role here in the last part of the calculation, which is our density is our mass, 48.0 grams, divided by our volume, 8 milliliters. And that's going to get us here again, 48 divided by 8, going to give us again 6. Here we want to think about significant figures. So the end here we divided. That means the top number here has 3 significant figures, as we figured out a second ago. Bottom number has 2 significant figures. That means in this particular case, I actually need to add a 0, right, with a decimal point there to give me the proper number of significant figures. By the way, what happens with these units? Do they cancel? They do not. So the number stays with the grams part, and it's always 1 milliliter. You need both units still there when it's all said and done. Yeah. Any questions on that one there? So again, it's important to keep track of those sig figs as you go through it, and also units as well. So make sure you have units on everything. And in this case, they don't cancel, so you got to keep them around at the end there. Yeah. All right. Now, when we're given the density in a particular problem, you can definitely use the density as a conversion factor. And as I was talking about a second ago, when we're doing dimensional analysis, you could actually take kind of a dimensional analysis approach to the problem. And you don't even have to worry about the equation d equals m over v, because if you just do opposites, it will kind of take care of itself as you're doing it. So what do I mean by that? Let's just take the density we just calculated there, and we had 6 grams per milliliter. What that basically means is I have 6 grams in 1 milliliter, and I could use it as a conversion factor of 6 grams over a milliliter, or you could flip it around, put the milliliters up on top and the 6 grams on the bottom. And now let's just say, for example, I had, 325 milliliters, and I want to know, how many grams that would be. I could just take a dimensional analysis approach with this without even thinking about the formula, to be honest with you. I know I need to get rid of milliliters, so all I have to do is this. And just like we did earlier, to get rid of those milliliters need to go on top or bottom. They need to go on the bottom, which means I'm just going to use my density like this. And because I set it up with my dimensional analysis, I know that will cancel. But even more important in this case is I know what's on top will get multiplied, right? And what's on the bottom, which there's nothing really here, would get divided. So I just rearranged my density equation in this case to solve for mass, which would be volume times the density, without having to even rearrange it. And I already know the math correctly. I know I should be multiplying and not mess up and maybe divide when I shouldn't. So again, you could take a more dimensional analysis approach, especially if you're given the density, use it as a conversion factor. And like I said, you don't even have to worry about really rearranging the equation or anything like that. In this case, though, is that the right answer in terms of significant figures? I'm going to go with no. Yeah. So here we're multiplying. That has how many significant figures? 3. Do I need to look at the density significant figures? I do in this case, right? That's 2 significant figures. That means really this guy should end up here, which means we do need to round. So that is 2,000 grams. Is that the right sig figs? No, that's how many sig figs? I heard a lot of numbers there. I didn't hear 1, which I think was the only number that we actually need here. 1 is actually here, right? It was not 4 because there's no decimal, but if I did put a decimal at the end, now there's 4, right? And that's still not the right number. This is a case, as we talked about before, the only way to get the right number of sig figs, a little scientific notation action, right? 1, 2, and 3 would be the correct number of significant figures and the right meaning for it. So definitely I would recommend that if you come across density problem, you have the density, I would take a more dimensional analysis approach, and it's sometimes easier than worrying about, did I rearrange that correctly, or should I be multiplying or dividing? So again, that is the benefit sometimes of doing things dimensional analysis way. A lot of times you could almost put some formulas to the side and not have to worry about memorizing them or rearranging them, and just kind of take that sort of approach. Any questions on that there? All right, so why don't you try one here? We are looking for the volume and we have the mass given to us of 14.7 grams. Once again, you absolutely can just use the density equation, just check things off. You got density, you are looking for the volume, and you have mass. So we could rearrange this and basically multiply the volume to each side. Come back and divide by the density. And that'll essentially give you that the volume is equal to mass divided by density. You could also, again, take a more dimensional analysis approach, and now I'm going to have to worry about rearranging that equation. And I know that I have a density like this, which means I could flip it around if I needed to and use it in this sort of fashion. And in this case, frankly, I have grams I don't want. So even if you're not sure where you need to go, you probably know you don't want the grams anymore. So I need to get rid of that. So that's going to be this guy right there. And milliliters are going to go on top, opposite with the grams. Grams will cancel. At this point, I'm left with milliliters, which is a volume, and that's what I'm looking for. And again, by setting it up like this, it takes care of all the math for you. I again know up on top gets multiplied, on the bottom gets divided. So I know I should be dividing this number, as that's basically up on top, right? That number there. And that is essentially what we got here, right? Without rearranging the equation. And the dimensional analysis took care of all that for you. That gets you 14.7 divided by 1.32. Going to give us a lot of numbers there. 11.1363636 milliliters. Significant figure wise, we do need to look at our grams, which is 3 significant figures. We do need to look at our density number, which is this guy, which is 3 significant figures. I'm going to go with 3. Seems to be a winner there. 111.1 milliliters in this particular case. Yeah. Any questions on that? So again, hopefully you can kind of see that if you set it up like this, it can take care of not having to do something like that, yeah, that you might not want to do in certain cases. Or you can still do that if you're comfortable doing that, and you'll get the same answer. Obviously, if you just obviously at this point plugged and chugged into there, you'd get the same answer as well. Any questions on that there? All right. And last one here. John took 2 teaspoons of cough syrup for a cough. If the syrup has a Okay, so let's take a look at it again. If we pull out the information, we got a volume of 2 teaspoons. We have the density given to us of 1.2 grams per milliliter. Again, the number stays with the grams part. It's always 1 milliliter. And we are looking for really the mass or the grams in this case. So again, if we take our density sort of formula and we just check off, we have density, we have volume. We obviously want to solve for mass in this case. We would multiply the volume to the other side. That's volume times density. Once again, here though, we can take a dimensional analysis approach and see how we do. We are also given a conversion in here of 5 milliliters is 1 teaspoon. So we have sort of that equality given to us here. And that's important because, again, we can use our density as a conversion factor. We could flip this around and go a milliliter on top, 1.2 grams on the bottom. Much like we talked about previously, though, our volume and our density is in milliliters, but it's in teaspoons here, which means we do need to do that conversion. So we can use this equality here to get it in the right units so that we can then use the density as a conversion factor. So we will do that first. 2 teaspoons, again, opposites canceling. We're going to go 1 teaspoon on the bottom, 5 milliliters up on top. That's going to cancel, going to give us 10 milliliters here. Milliliters in this particular case as our volume. We now have really our volume in the correct units to use the density and a dimensional analysis approach. Here, this is 2 sig figs, by the way, right? And 2 sig figs. We do need to look at the 5 here. And we should end up with two significant figures. That's why I got rid of the 0 there at the end. Now that I have it in milliliters, I could just take a dimensional analysis approach and get rid of milliliters, which means opposite's going to do that for me, which is that density conversion basically right there, 1.2 grams per milliliter. Those are going to cancel. We're going to multiply in this case, and that's going to get us a 12, I believe, grams in this particular case. Any questions on that one? Again, significant figure wise, this guy has 2 sig figs based off of obviously back here. This density we do need to look at has 3 significant figures. Once again, here we're multiplying, and that means we should end up with 12 in this particular case. Don't really need a decimal, put it in there for free. Yeah. Any questions on that? Or density? Obviously, you could just plug and chug into the density equation if you have the mass or the volume given to you. Any questions on that there?